So this time we're adding HCl. So we're adding an acid, right? So we need to write a different equation when we write our moles table. And again, you see this? Not a nice table. So if the added chemical is a base, like we did before, you write a reaction with OH plus HA. But if the chemical is an acid, then you write the equation for H3O with A minus, right? So because this is our base now, that's our base, that's our conjugate base. So we need to write an acid plus our base. And so here we are as our base. And again, I'm going to show you this one, right? Again, if you see here, this K is here, right? I don't care about the K. I'm only looking in the ionic terms, right? So we have our moles table. So we just look at what's given to us. We have 0.07 of our, oops, that's our F. This, and I said we added 0.2 moles of H3O, right? So that's what we got. So the question is, now again, Chateliers, we think about this one. So with or without an equation, if you add the acid, it's going to react with the base, right? So if the acid reacts with the base to make, in this case, it's going to make conjugate, or it's going to make our conjugate acid. In this case, it's just our acid. Here's this H3O is going to react with this, right? I'm going to draw a little Le Chateliers. If I increase this, it's going to shift that way, which will decrease that F. So that means that this F is going to go down by 0.2, right? So it's going to go down by 0.02. And it's going to increase the amount of our HF, which our HF is going to go up by this much. So here it is. So here's the amount we added. None of it's left, right? So this is 0.07 minus 0.02. That's what gave us our 0.051, right? Because we added this, which made this go down and this go up. And then this went up by this amount, right? And again, this is a moles table. And luckily, sorry, let's put this on here. Here it is again, just in a bigger way. And so again, here's what happened to it. So this went down by H3O. This reacted with H3O. This created more HF, right? And then thankfully, yay, look, 1 liter. Easy peasy, our molarity is the same. Again, if it's not 1 liter though, it is not the same. You need to be careful of this last one. So again, this is a moles table, not an ice table. But now we can do an ice table. So at this point here, you can just use Henderson-Hasselbalch if you choose, because you have your HA and you have your A minus, and you can just use Henderson-Hasselbalch. I have to give you the K though, which I think I gave. There it is. So here's again, all I did was here's our new, which again, same thing, you don't even need an ice table. You just use these calculations. I must have told you that the pK was 3.15 earlier, 3.15, and again, F minus over HF. Okay, so same problem. We just did this different problem. We just did 2 of them. The new concept here was that moles table, right? And that moles table gives you a little trouble at the beginning, but if you use your knowledge with Le Chateliers, you can think through what's going to happen with that new moles table. Okay, now basic buffers. So basic buffers, very similar to acidic buffers, right? So if you have a basic buffer, it's just a weak base and it's conjugate acid, which is exactly the opposite. So you can make a lot of buffers with, for example, ammonia, right? But ammonia, a lot of times like your lab book says use ammonia, and on the piece on your little dropper says ammonium hydroxide, same thing, right? Because they're in equilibrium with each other. But you can actually make kind of a great buffer solution with that. Okay, so now Henderson-Hasselbalch is written for weak acid conjugate base. So Henderson-Hasselbalch is written for like acidic buffers, but you can still use it for basic buffers, right? And so you can literally, I'm going to show you, you can just use it here. You can use it like this. I'm going to show you an even better way to use this in just a second. Just a little mathematical little trick here. But you can use it for buffers. You just have to switch these two, right? And so I'm going to look at this. So pKa and pKb. We talked about the difference between Ka and Kb, right? We said Ka times Kb equals Kw, right? We did that Tuesday. Well, pKa and pKb works the same, right? So I'm just going to show you how this works exactly the same, right? Remember we said like H times OH, right? That equals Kw. And then if you took the negative log of H, negative log of OH, you get 7 plus 7 equals, right, 14, because it's 10 to the negative 14th. You can think of it the same way with our pKa. And again, if that doesn't make sense to you, I'll show you right now. So Ka times Kb is Kw. You take the negative log of them, it equals 14, sort of just like we did with our pH. And therefore, if you take the negative log of Ka, right, and remember the definition of pKa, pKa is the negative log of the Ka. So if you take the pKa, and guess what, pKb, same thing, negative log of whatever is behind it, equals 14. So pKa plus pKb equals 14. So if they give you pKa, but you need pKb, you just subtract 14, just like we do with POH, right? Same exact mathematical principle. We're just going to do it with pKas and pKbs now. Remember, P just means negative log of. So when you see this, this is negative log of the Ka, negative log of the Kb. Just like when you do pH, negative log of H, POH, negative log of OH. Okay, so now, in this case, I'm going to show you how to do this in two different ways. So what's the pH of a buffer? That is 0.5 ammonia, give you the pKb, and 0.2 ammonium chloride. Now remember, chloride, I don't care, right? Do not care, is not important. All we see is the net ionic here. Now again, this equation is very important, right? So you need to know this equation because this equation is going to tell you a lot of times. Again, the most common mistake here is people don't know if their X's are H's or OH's. But when you write this equation, it's going to tell you your X is an OH, you have a base, right? Okay, so now we can find our pKa by just taking 14 minus our Kb. There is our pKa. And then we just plug it in, knowing which are pluses, the minus goes on top, plus goes on the bottom, or not the minus, the base goes on top, the plus, the NH4 plus goes on the bottom, and you get 9.65. And then we have to, again, check that X is small. And again, here it's H3O plus we're looking at. This is H3O plus because this is pH. So we need to put this over our initial acid concentration, right? And again, this is our conjugate acid, but it's still our conjugate acid, and that is less than 5%, so we know we're good. But I'm going to show you another way to solve this. So personally, I like to keep my acids and my bases separate. I don't like changing my bases into acids, right? So what we did is, this is all about acids, right? Henderson-Hasselbalch. I like to keep it as base. And so I'm going to show you how you can use this and keep it as your bases with your bases and your acids with your acids. So what you can do is we can just rearrange the Henderson-Hasselbalch equation and we can make it with POH. So all you use is your pKb, and then you just do just like you did, it's just like your conjugate acid over your base. And this way you don't have to change it into pKa. So I'm going to go back so you can see the difference. So you see here's our regular Henderson-Hasselbalch. Base over conjugate acid. and it's pKa. I'm going to change this to pKb, and then you just flip these two. And there you are, POH. Now, I'm actually going to have to exit out of this so you can see something for a second. Oops, hold on 1 second. I just want to go back to, actually, no, I'll just write it on here. Okay, so our regular Henderson-Hasselbalch, I'll see if I can get it all on here, is pH is pKa plus log of A minus over HA. I got it on there, right? So what I'm trying to show you is for a base, you just kind of flip everything, right? So instead of pKb, you flip to pKa. Instead of HA on the bottom, you flip it on the top. So you don't have to memorize. What I'm trying to tell you is you don't need to memorize 2 equations. You just flip everything for your base, and you end up with your POH in the end, subtract from 14. So you don't need to memorize 2 different Henderson-Hasselbalch equations. You just need to know one, and then if it's a base, you just flip everything. Okay.
Oh, can't see the formulas. We see you doing hand motions.
You can't see this right now?
No, it's just you.
Okay, hold on. It's like my computer just really hates me. Sorry. Try this again. Oh, and I can see your chat now. Zoom updated, and it's like my computer and Zoom are literally like at odds with each other. Let me try this one more time. No, it's not working at all. Okay, there we go. Can you see me writing now?
Yeah.
Okay, good. Okay, so I'll try this again. And it was so nice before. Okay, so the regular Henderson-Hasselbalch is just pH equals pKa plus log of, let's see if I can write this nice enough. A minus over HA. There. Really tiny, hard for me to write. Okay, so what I was saying is you don't need to memorize the base way. You just need to remember that everything is flipped, right? So instead of it being pKa, it's just pKb. And so instead of it being A minus on the top, right, your base goes on the bottom, you just flip it, right? So you just flip everything, and then you have POH here. So the equation, the one we just did, which was 0.5 and 0.2, right? So I'm going to show you, and this is adjusting, this is making a base conform to an acid formula. So now we're just going to do the exact same thing, 0.5 and 0.2, but this time I'm not going to make it conform to the acid Henderson-Hasselbalch. I'm going to flip everything, right? And so when you do this, it's just the pKb, and then remember it's HB over B. So it's the actual acid form over the base form. So you just kind of flip how you would normally do it, and you end up with POH. Now, you can still check if your X is small here, but since this is your POH, when you take 10 to the negative POH, right, that's your hydroxide concentration. So when you do X is small, it needs to be over your base, right? Before we did X is small, we put it over the conjugate acid. It doesn't matter which way you do. I just personally like to keep my bases as bases and my acids as acids, right? You just can't forget here, you need to subtract from 14. But you end up with the exact same pH. So I'm just going to go back so you can see this really quickly, how I did this differently. So before, again, we just adapted our base to the Henderson-Hasselbalch regular. We got our pH. Then we took 10 to the negative, and that's our acid concentration, right? And so we put that over our conjugate acid concentration. Bases stay with bases, acids stay with acids. This is an acid. So we put this over the acid, okay? Now, I'm going to go back here quickly. 10 to the negative OH, this is a base, right? So we put this over the base, right? And you can solve it either way, whichever way you choose. It doesn't matter to me. As long as I can follow your work, I don't care. Whichever way works for you. Okay, so we did acidic buffers and we did basic buffers. So your brain's probably gonna hurt a little bit after this, but it's actually kind of fun at the same time. Now, let's look at buffering effectiveness. So a good buffer can neutralize a lot of acid or a base. Right now, how do you know what a good buffer is or not? That's what we're going to talk about. And so again, eventually, you can add enough acid or you can add enough base where your buffer is no longer effective, right? And so buffering capacity, that's just how much acid or base it can neutralize, right? So that's like how effective your buffer is. How much acid can you add? How much base can you add before it's not a buffer anymore, before you overcome it? And again, it's just really fun to do in lab. Okay, now the buffering range, this is the pH range that you can use the buffer, right? And so we're going to talk about what that is in just a second. And now my computer's not working. Okay, so the effectiveness of a buffer depends on both how much acid or base you can use before it becomes ineffective, and the concentrations of your acid and your base. So let's look at these. So I have two buffers, right? And my first buffer, I have 0.1 mole of my acid and 0.1 mole of my conjugate. Buffer 2, I have 0.18 mole acid and 0.02. Do you see how the big difference in these concentrations here? Very big difference in these concentrations, right? 10 times difference. Okay, so I look at my first buffer. I do my little moles table. So what I'm going to do is I'm just saying I'm adding NaOH. So I'll walk through this slowly because it's, again, just like we just did. So if I add NaOH to this buffer, I add my NaOH, my hydroxide, my base, is going to react with my acid. So my base is going to react with my acid. So my acid is going to go down by the amount of base I added. The conjugate will go up by that amount, right? Just think of this as what we just did. This is like our acid plus our base makes salt and water, what we just did before. So then we have our new moles. We're just going to assume it's 1 liter. Okay, we're just going to say it was 1 liter, which, by the way, Henderson-Hasselbalch works with moles. It's lovely, as long as it's 1 liter. So 5 to 5.09. Do the same thing here. Again, we're adding OH. So we have 0.01. So this is going to go down by 0.01. This is going to go up by 0.01. And again, we'll just assume 1 liter. Put it in the Henderson-Hasselbalch. Hold on, it's coming. Soon. There it is, 5.18. Wait, that's not the right one. Well, I don't have it. My Henderson-Hasselbalch's gone. I'll just write it in here. So pH equals 4.05 plus the log of my base, which is 0.03 over 0.17, and the new pH is 4.25, right? So you can see the change here is much greater. So these differing concentrations made for a less effective buffer because the buffer changed a lot. So here's another buffer. And again, same thing we just did pretty much. This one is 0.5 and 0.5. Here's my initial pH is 5. I'm going to add OH. Changes to 5.02. Barely changes. I'm going to do this again. See the difference here? These are much more dilute. And you can see here the change is 5.18. So the other one changed, it was 5.02. to 5, and this was 5 to 5.18. So the first example I just showed you was varying very different concentrations of the actual acid and its conjugate. The second one I showed you is dilute versus more concentrated conjugate and acid. So if we look at the percent change here, the first one only changed by 0.04%. So like I said, barely changed. And the second one changed by 3.6%, right? So there was a greater change when the concentration was lower. So it's most effective when the concentrations are the largest. So the more concentrated that acid and its conjugate are, the better the buffer is going to be. So that brings us to buffering capacity, right? So a concentrated buffer is going to be a better buffer because it can neutralize more acid than base than a dilute buffer, which means you can just add a bunch of acid and you won't see a change, or add a bunch of base and you won't see a change when it's concentrated, versus if it's really dilute, a little bit of acid and a little bit of base will make a bigger change. So a better buffer is a concentrated buffer. And so how do we like quantitate this, like make this so we can actually like use this versus just have it in qualitative terms? So when the ratio of base to acid is 1, so when they are their concentrations are very similar, it's a very good buffer, right? Now, how do you know if a buffer will be effective? So it's like 10 times one way or the other. So here's the equal concentration and here's like 10 times, so a 10 times difference on either way, right? So either your base is 10 times less than your acid, or your acid is 10 times more than your base. So, and we're going to look at this in just a second. And then the other one is a buffer will be more effective when the acids and bases, when the concentrations are large, right? So highly concentrated. So we said that a buffer will be more effective when it's either 10 times either way. And so I'm going to show you a really easy way using Henderson-Hasselbalch. So I'm just going to use ratios here. So the lowest pH, right, that would make this ratio 0.1, 1 over 10, right? 1 over 10, 10 times, right? So that makes the pH pKa minus 1, or 10, this is a 10, this is a 1, plus 1. So how do you know if it's an effective buffer? pKa plus or minus 1. That's how you know. So if the pH is within plus or minus 1 of a pKa, you've got a good buffer, right? That's a good range for your buffer. Okay, so when choosing an acid to make a buffer, you want to choose one whose pKa is closest to the pH of the buffer. Okay, so one more, this is it, and we'll probably maybe a tiny bit more, just because I'm sure your brain's kind of hurt. So, which of the following acids would be the best choice to combine with sodium salt to make this buffer? So, I've got an acid. It's a weak acid. Its pH is 4.25. Now, I have 4 choices. Which one would be the best choice to use with my buffer? What do you think? Which one's the best choice? Yeah, the third one, because it's closest to my actual pH, right? And so you're looking for this, it's actually a lot easier than the math is. It's just if your pKa is close to your pH, that's going to be your best buffer. That's going to be your best buffering range. Okay, so now, okay, we'll do this one more because your brains are going to hurt if I do any more than this. They probably already hurt, sorry. Okay, so what ratio, and this is nacho to hacho, right? That's, we'll just say it like that, would be required to make a buffer with a pH of 4.25. So we just used Henderson-Hasselbalch and we solve for the ratio. So we're just going to solve for this, right? So if we do this, here's our pKa, here's our pH, and then we just solve, right? So if we do this, sorry, I'm just going to plug those in, and I'm just going to literally solve for this ratio. And so remember, you just take 10 to the of it, and then here is my ratio. So this ratio means I need 3 times more of this than this, right? So I need 3 times as much of my nacho than my other one. And again, remember, I'm just ignoring this. That's why it's like popping on there sometimes or not, because remember, we're always thinking in terms of net ionic. Okay, so we'll start with this one tomorrow because this is going to hurt your brains if I keep going. Okay, so we're going to end there today.